Homework 13, page 186. We're skipping section 3.7, like I said. We're going to 3.8. And now 1 through 5 odd, skipping to 11 through 43 odd. That's 20 problems. That's a lot. They're all word problems. So yeah, and so do not delay. Get on this right away, right? It's going to take a long time. I know that. Okay, so let's look at, here's a word problem. Okay, so we have a 5-foot ladder leans on a wall, okay? If the bottom of the ladder slides away at 2 feet per second, how fast is the top sliding down? So here's the ground, right? Here's the ladder. It's doing something like this, right? That's the idea. That's the setup. This thing is, it's touching like that, right? And slides down like that. Now, if you're like me, you think, well, if the bottom's moving at 2 feet per second, the top's moving at 2 feet per second, right? That's what you'd think. And you'd be wrong. And so let's draw this out. So with all of these, first, and like I've said for 2 years now, the first step should always be draw it out. So there's your wall, there's your ground, okay? You have a 5-foot ladder that's sliding down a wall, okay? So something like this. That looks like a right triangle, doesn't it? Maybe that'll have something to do with it. So, 5-foot ladder leans on a wall. The bottom of the ladder is sliding out, okay? The top is going down. So what I'm going to do, so let's think about what they're asking me for. We want to know how fast is the top sliding down. We want to know. So I'm imagining there's a point right here and a point right here. And we want to know how fast is that guy moving. And what I'm going to do right away is give these points names. Because I imagine as this moves, this point, which I'm going to call X, because it's on the X-axis, it's moving to the right like this. And so what I'm going to do, I'm going to think about this point, I'm going to call it X of t. Because as time goes, X moves. It's a function of time. And you're going to see that with almost all of these. Almost every single one of these is going to be, we're talking about rates, and that's almost always with time. Now, technically a rate could be, you could have like dollars per customer or something like that. That would be a rate. But here we're talking about usually like motion or something with time. Something per, per unit time. So that's what's going on here. Anyway. So X is moving this way, and Y is moving that way. I'm going to call this point here Y of t. Both are functions of time. Now what I want to try to do is, so first off, so that, okay, let's see for all the given information. A 5-foot ladder, so that means that this length right here is 5. Okay. Leans on a wall, bottom of the ladder slides away at a rate. So what would that, in terms of X, what would the rate be?
X of 2.
X prime. The derivative of X.
Oh,
right? It doesn't say at 2 seconds, right? Because t is in, I guess, seconds. Yeah, because feet per second. This is saying it's moving at 2 feet per second. And so whatever the value of X is going to be that distance right there. It's going to be the number of feet that is at any given time. And so, like if you think about it, if X is moving at 2 feet per second, it's going to look like, your X function is going to look something like this. It'll have a slope of 2, I guess, right?
Yeah.
And it's, yeah, I mean, we don't need this, but I'm just thinking about it, right? And if the output of X is in feet and time is here in seconds, then its rise over its run would be in units of feet per second. That's what that's telling you right there, is that the derivative here at the time we care about is 2 feet per second. And in fact, as a matter of fact, it's a constant 2 feet per second because it says it slides away at 2 feet per second. So, I mean, you could then infer that X of t must be 2t. That's the only way you could take the derivative of a function and end up with 2.
Yeah.
unless it's 2t plus a constant, you know, something like that. But anyway, that's not really, we don't really need to get into that for these problems, but it's something to think about. But anyway, okay, so this is just the given information that we know. Now, one way of dealing with this is to actually explicitly write functions in terms of time, right? X of t is, and we could do like what we just did, right? X of t would have to be 2t. Y of t, I guess, would be unknown, whatever, blah, 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 blah. And then get everything in terms of time and take derivatives and stuff like that. But with a lot of these problems, that turns out to be more work than is necessary. What we're trying to do here is figure out, so we need, what we're looking for is how fast is the top sliding down. So what we want then is y prime, right? And we want to know, and there's something interesting going on here, when it's 3 feet from the ground. That leads me to believe that it's not the same always. But we'll get into that. We'll get into that. So anyway, the idea is we want y prime of t. Now, just looking at this, if this length right here is x, and this length right here is y, that's a right triangle. That's the hypotenuse. Can we get an equation from that information?
X squared plus y squared equals
There you
5.
go. X squared plus y squared equals what?
5. Oh, root 5.
How about 5 squared? The other way around. 5 squared, right? Pythagorean theorem. Now, here we go. We just did implicit differentiation. But in implicit differentiation, we assumed that y was a function of x, and we took the derivative with respect to x of everything. That's not quite what's going on here. In this case, everybody is a function of time. It's still implicit because we don't have the actual formulas for whatever x is and whatever y is. But the principle is still the same. That this is some function of t, we don't know what it is. This is some function of y, y is also some function of t, we don't know what it is. But again, it doesn't ask us to write an equation for y or an equation for x. It's only asking us, really, we just want to find the derivative at a given time with given things. So what I'm going to do is I need to make a y prime pop out somehow. If I just take the derivative with respect to t across the whole thing, that should do it, right? So let's do that. I'm going to take the derivative with respect to t of both sides. d dt over here. The right-hand side is what?
0.
Which is 0, which is nice. Now, take the derivative of this with respect to t, and what happens?
2x x.
There you go, right? 2x, x prime, and I'm not going to write the x of t, though that's what it is, x prime, plus
2y.
2y times y prime. Now, that's the thing I want to get by itself, very much like last time, right? First thing I'm going to do is isolate this guy. 2y y prime equals minus 2x x prime. Dividing by 2y gives me y prime equals, the 2's are gone, it's still negative up in the top, and a y comes downstairs. Now here's a question. Do we have enough information to get all this stuff in? So x prime, we already said, is always 2. So that part's done.
You get an equation for y.
Yes, so we actually were given y, because look at this part right here. How far is the top sliding down when and it refers to this point right here, when that's 3. So in other words, y is 3 at this time. Again, we don't have to solve for time. We could if we wanted to, and we could find out, like, if the question was, when does this happen? Although there's not enough information because it didn't tell you when it starts to move and how far it was. Like, did it start straight up and down? I don't know, nobody told me, right? But now, how do we find this bit right here?
Need 3 squared plus x squared equals 5 squared.
There you go, right. This is the x that we care about is going to be x squared plus 3 squared equals 5 squared. So 25, 9, x squared is 25 minus 9. That should be 16. So that means that x is 4. It's not negative, the way I've set it up. And so that means that the x value at this time, which we don't care what time, in this case we could get it without finding the time, so who cares, right? So at this time, we know that x is equal to 4, the y value is equal to 3, and x prime is always equal to 2, so we got it. This is what we care about. We get y prime, that is the rate at which the top is moving, is equal to negative x is 4, times x prime, which is always 2, over y, which in this case is 3. So we get y prime at this time is negative 8 thirds. Now, let's just real quick. And so that's the answer to the question. That's how fast it's going. Negative is good. It should be negative because it's moving down, right? As x gets more positive, y moves towards the negative. And so that lets me think, okay, at least I set this up right. It should be a negative number, right? The negative tells you the direction that it's moving. And since I called this positive 3, right? I could have set this up differently. I could have set this up on some crazy axes where it's down here and it's moving this way. But the way I chose to set it up, y is a positive number and it's becoming less positive. And so that means it's decreasing. Its derivative is negative. Its slope is negative. Does that make sense?
Yeah.
Okay. So one more thing. This is key here because for a few reasons, we couldn't plug everything in if they didn't give us when that happens. But the interesting thing here is to notice that if the time, or if it weren't 4, it's not a constant negative 8 thirds, unless it might be. Hold up, let's see. So, actually, I don't want to go into that right now. It's just something to notice. Like, we could, if we wanted to, get all of this, say, in terms of y. We could come up with an explicit x. Let's say that we knew that it started at time 0, it was straight up, and then it moved at a constant 2. Then that would be x is 2t, like that, right?
Yeah.
Then we'd also know that it's at 2 seconds. That's how long it took, would be 2 seconds. In which case, then this gets a little bit different. So, first off, this is the way I suggest that we do it. Okay? But it's possible to do this a little bit different. Where we say, okay, since x squared plus y squared is equal to 25, then we could get y by itself by going 25 minus x squared. Y is a positive number over here, so we're going to take the positive 25 minus x squared. But we know that x, in this case, if we knew all that stuff, we could say, okay, then y of t is equal to root 25 minus 2t squared. Now we just take a derivative. So this is another way you could do it. Again, though, the problem with that is we don't know what time. It didn't give us the time, so yeah. But let's go ahead and just figure this out. So now, if we know our y of t, and another problem with this, or another, it's not a problem, it's just that now we also need to know what time this occurs. Because it's asking us, when is this thing 3 above the ground? Well, that would mean, and we'd have to go through and say, well, that's when the bottom is 4. When is the bottom 4? In other words, when is x of t equal to 4? Well, since that's 2t, when is that equal to 4? Well, it must be that when t equals 2 is the time that you care about. So that happens when t is equal to 2. And so here's my function, which gives me y at any time t. And so what we care about is y prime of t. So if y of t is equal to root 25 minus 2t quantity squared, then y prime is, okay, the root comes down like this, and we do a 2, right? 25 minus 2t quantity squared. Then we take the derivative of the inside stuff. The derivative of 25 minus 2t squared is going to be, the 2 comes down, negative 2 times 2t to the first times 2, right? Because the derivative of 2t is 2. So minus, and I'm going to write it like this actually. So minus 2, how about 4t times 4t? Why did I do that? Well, because the 2's cancel. Okay. All right, so moving on, that gives me negative 4t over root 25 minus 2t quantity squared. Now we did the work and said that happens when t is 2, so I want y prime of 2, so I plug in a 2, I get my negative 4 times 2 all over 25 minus 2t would be 4 squared, right? 16 minus 16. 25 minus 16, I believe, is what, 9?
Yeah.
And square root 9. Ah, nice. Cool. Okay. Neat. Here's the why did I do? Well, one reason I did this is because this is another way of solving it. I, for the longest time, refused to do it this way. I would only set it up like this. I don't know why. Something in my head said, I want a function of t. I want to know when I plug in a t, I get this out. But you do have to do a lot more work, right? You have to use your brain, come up with something like this, which we don't know if that's the case. Was it the case at time 0? It was all the way up? We don't know. So, right? And are we sure that that's the case? Yeah, I guess. So the implicit, I guess I erased it all, but the implicit function way does make it a lot easier to solve, although this way makes me feel good because I have an actual function I can work with. But there's just something to notice here. Let's just look at y prime. Does this look like, so y prime we said was this guy right here. Does that look like a constant to you?
No.
No, as t changes, this guy changes. So he's not going down at a constant rate. Even though x is moving at a constant rate, this guy is not moving at a constant rate. I think that's very interesting. In fact, you could say at time 0, plug in a 0 here and here. You have 0 over root 25. That's 0. So at the instant it begins, this guy's moving at 2 feet per second. The top isn't moving at all. Then as time goes, this guy does whatever he does. He eventually gets to minus 8/3, but it's clear that that is not a constant rate, which really messes with my head. That's not what I expected. Like I said at the very beginning, like, well, if that's moving at a constant rate and it's 2, the top should move at a constant rate. But we've just seen that's not the case. That's interesting. I don't know about you. That's interesting. So, you got this? Your homework's going to be very much like this. Just question after question after question like this. And I'm going to try to do a representative sample of what you're going to do. And all we're going to do is just work through stuff. So, no real theory today, right? We're just trying to get through these. So, these types of problems are called related rates problems. And the idea is, just like in the first case, we had some phenomenons happening, and we have a rate in this direction. And over here we had a rate in this direction, and we wanted to know how are these two things related. And so, in other words, we want to compute the rate of change in one quantity in terms of rates of change of the other. And we saw that that's what happened. We had y prime equals negative x times x prime over y. And so that's how those two rates were related. You got the rate of one movement in terms of the rate of the other. And usually to do this, we're going to find an equation that relates the two quantities themselves, right? So we found an equation that related the actual quantities themselves. And then taking the derivatives makes the rates pop out. And when you treat these as functions of time, right, then that's how that works, right? Okay, so these are related rates. Section 3.8, the section that we're in, has great examples. And so if you're caught up on something, there's probably an example of something similar to it here. And they do a really good job of going through it. I love this book. I think they do great. So, okay, here we go. So we're just going to do example after example. Here's number 4 from this section. And it tells you that the length, I'm just going to use L, cursive L for length. The length of a rectangle increases at a rate of 8 centimeters per second. Okay. Now, the width of the rectangle, is it increasing or decreasing? It is increasing at a rate of 3 centimeters per second. And what we want is when the length is 20 centimeters and the width is 10 centimeters, how fast is the area increasing? Okay, so what's the first thing I want to do? Draw it out. Okay, so I'm going to make length this way. We have some rectangle, and it's changing. It's obviously it's getting bigger. Okay, we have its length right here. I can't let myself do that. I got it. There we go. L, and we have its width right here. Now, what quantity do we want?
Area.
The area. And so the area is equal to, there you go, the area is equal to the width times the length. Now again, these are all functions of time, right? So in other words, what I'm saying is area of time is equal to the width time times the length as a function of time. Now all we need is just a prime, basically. So what do? Take the derivative. Just take the derivative in this case. And so we get a prime of t is equal to what?
W prime times L.
There you go.
Plus W t times L prime.
There you go. L prime. Okay. So now let's look here. Do we have all of that information?
Yeah. Well, not.
Don't we? L at the given. We don't know what time.
Yeah,
we don't
we
care.
have L in the-
And we don't care what time. But we know that when L of t, when L is equal to 20, so here I'm just going to start filling stuff in. There's L of t is 20. W is equal to 10. What's W prime?
We might come back, but I'll still keep them occupied and you guys do something else. You're not here.
So what is prime? Prime is the derivative of, which means, or the change in W. How fast is W changing? Is that up on the board somewhere? W?
No, 3.
3, right? So in other words, this is W prime at the time you care about. Okay. Okay. And this guy right here would then be L prime. That is how fast it is. And so we have a 3. Here we have L prime is equal to 8. This comes out to 60 plus 80, which is 120?
140.
140, yep, that's what I got. 140 watts.
Square centimeters.
Centimeters squared.
Per second.
Good, because area itself should be, so width is in centimeters,
Oh, but area,
length
right.
is in centimeters. So we have centimeters times centimeters, which is centimeters squared. And so this is some function, I don't know, it probably looks something like this. Okay, this is the area function as a function of width and length, or I guess time, or, well, I guess it would be increase. Who cares, right? But the point is, the output of area is centimeters squared. Time is in seconds, and so its slope will have units of centimeters squared per second. Not second squared, second. Okay, so I want to see units, please, on this one, okay? So, there you go. That's pretty easy.
Yeah, that
Now,
one's easy.
say what now?
That one's easy.
It is pretty, yeah, this one was easy. It's number 4. So, so now another thing, just to think about notation. Right now it might seem, and like I said a minute ago, when I first started these, I would always get it all in terms of one thing. Like I would turn this into a function, turn that into a function so that I have like an actual W of t equals, I guess its rate would have to be 3 times, let's pretend it started at 0 or whatever, it wouldn't matter. L of t, it's moving at a rate of 8, and we're assuming it's constant. You see, that's a problem here. It doesn't say it increases constantly. It's just saying that it's doing this when this happens. It might have been the case that it was doing this, and we just didn't know. Who knows, right? But you could do this, and then you just multiply those guys together, blah, 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 blah. And so, but I suggest it's good to do it other ways as well. Another thing I'm going to suggest is we've been using prime every time. It's good to also use this. We want dA dt. And so we take the derivative of the first thing, leave the second thing alone, dw dt times L, plus take the derivative of, or leave the first thing alone, take the derivative of the second thing, dl dt. It's good to be able to switch back and forth between the prime notation and the d notation. Because like right now, probably for the rest of this class, this won't be all that helpful. Maybe later, it might be helpful. But later on in calculus, like when you're doing multivariable, this is indispensable. You will absolutely want. So it's good to familiarize yourself with this notation here, and maybe every other one you do it one way or whatever. It's just going to help you. It's not going to hurt you if you don't, but it will help you if you do. And so we could say, okay, this is the derivative of L, which is dL dt. This is the derivative of W, so this is dW dt. Different notations, they mean exactly the same thing. So, anyway, that's my spiel about that. Any questions on that before we move to the next example?
No.
Oh man, this is one. Ooh. Oh man, these. Okay. These are rough. This might be the roughest one that we do. Maybe not. We'll see. It's number 14. At noon. So now they're giving us a time. At noon, ship A is 150 kilometers west of ship B. Okay, so we have 2 ships. One is 150 kilometers west of another one. We're assuming that, that means like that they're at the same height. One is west, one's here. Okay, now it says that A heads east at 35 kilometers an hour. Kilometers per hour. Okay, so A is heading, let's see, well, we'll set all this up in a second. B heads north at 25 kilometers per hour. Question: how fast is the distance between the ships? Those put distance between. How fast is the distance between the ships changing at 4 p.m.? Okay, let's draw this up. This one's a doozy. So we are given north, east, south. So I'm going to go ahead and set it up this way. So here's east, west, north, south. It's almost always going to be helpful to have one of your things at the origin. So we'll do that. Now I could put the other ship over here, west of that ship. But then I'm dealing with negative numbers. I don't want to do that. So I'm going to put the other ship here. And so A is west of B. So which one's A and which one's B?
A is the origin.
A is the one with the origin. Okay, so here's ship A. Here's ship B. And at the time where they start, at the starting time, at noon, we're going to call that time 0, right? Time 0 is noon. Then they are 150 kilometers away from each other. So another way of saying that is that B is at 150, right,
Yeah.
on the x-axis, or on the x-axis, etc. Okay, now let's think about what happens here. And what I like to do when I do these, I draw arrows for the rates. So I'm going to go ahead and think about this as A of t is going to be the position of A. And then therefore A prime of t is its speed, or its velocity. Okay. B of t is the position of B, ship B, and therefore B prime is its velocity. Okay. Now A is moving which direction? A heads east, and so that's this way. And I just like to do little arrows like this. I'm going to say, okay, so A is moving this way at a rate of A prime, it says it's 35. B is heading north, so that's up at a rate of B prime is 25. Okay. Now, here's the thing. So, this is not the picture we want. Because at the time that this is happening, right, they're not 150 away from each other. So where is this one after however many hours?
35 times 4.
There you go. Okay, good, good. We know it's going 35 kilometers per hour. How many hours have elapsed? 4 hours have elapsed. The hours are going to cancel, and we get 35 times 4 is 140. 140 kilometers this way. So here's my second picture. East, north. So he's moved 140 kilometers this way. So now A is at 140. Still moving in this direction. B, where is B at this time?
100.
At 100, right? Because he's going 25 kilometers per hour for 4 hours. There you go. And that's 100 kilometers. And so he's 100 kilometers north of where he was. And this will not be drawn to scale. Okay, so now, this is where this is going. So you think, okay, find where they are. There. We have a nice right triangle. There's that. There's that. And so first off, what is B started here at 150, right? And so this is 150. And so then what's the base of that triangle?
10.
10. Okay. So we have a right triangle. 10, 100. We could find what that is. And so you think, okay, we got the triangle. Let's just do what we did last time, right? Or do what we did the first time when we had it's just like the whatever. Oh, and the distance is the thing we care about, right? That right here is the thing we care about. What we want is a d of t right there. So there's d of t. And so what equation is going to give me that?
Square root 10 squared plus.
Well, yeah, oh yeah, yes, you're right. But what I was thinking was just dt squared is equal to 10 squared plus 100 squared. You agree with that?
Yes.
Now, take the derivative with respect to t.
Just
2d times d prime. What's the derivative over here? Uh-oh. Then it doesn't matter what the distance is. We could tell the distance is something. In fact, we could actually compute the distance if we wanted to. But we would, whatever it works out to be, which actually it works out to be 100 point something. Where is it? Where'd it go? Sorry. Oh, 100.499. At this time, it's 100.499. And you could do that just by plugging into this, blah, blah, blah. So you get 2 times 100.499 times d prime, which is the thing that you care about, is equal to 0. You divide, and you get, oh, but that can't be. That can't be the case. It cannot be 0, because they're still moving, aren't they? Right? They haven't stopped. They're still moving. So what happened? Well, in this case, so in other words, if you get to this point and go, oh, that doesn't make any sense, then you need to bring out the big guns. And by that, I mean, what we've done here is we've assumed, well, the problem is that there's no t's over here anywhere, right? Like, yes, this is what it is. That is what the distance is at 4, right? So in other words, d of 4 is equal to that, so that the distance at 4 is equal to the square root of this. But basically what you've done is you've plugged in your value and you got out a constant.
Yeah.
We don't have the function itself. We need the function in terms of time. But we're also going to need this. This works out to be 100.499. And so that's nifty. We're going to need that in a minute. But we're also going to need actual explicit functions for A and B. And so, and it's not, and here's the thing. Like, when I was first doing this one, I thought, okay, I guess they're going to need to be like coordinate functions, because A starts at 0, 0 and moves to 140, 0. But that's, you don't need to do that. That's a bit too much. Really, all we care about are these lengths here. And so, don't worry about the 2D geometry of this. Really, all you need is an A of t, which tells you the length of this thing. And it's the length of this. We don't care about where he is here, because it's not this length that we're trying to find. We care about this length here. So, A of t, let's think about it. When it's 0, it starts at 150, right? And then we know that this distance is shrinking as time goes on. And we know it's shrinking at a constant rate.
Yeah.
So that means that my function here, my A of t, should start here at 150 and move down like a line. What should the slope of that line be?
35/1.
Well, how about negative 35,
Yeah.
right? It's because that's decreasing, we expect. So how about it starts at 150 minus off 35t. That would give me what I want here. Does it work when I plug in a 4? Because when I plug in a 4, it should give me out a 10. You see what I'm saying?
Yeah.
Right? Because now, what you could do, like let's forget about this problem altogether. And if all we cared about was just the position of A, you could say, well, A, it starts at 0, so there's no plus anything, right? And it moves at a constant rate in the positive direction at 35, so that would just be 35t. And you'd be right. But that's not, so technically, I guess that is A, but what I'm calling here is this length there. That length is shrinking at the same rate. And so something like this is going to have to be involved, right? If you're completely lost, what you could do is say, they've given me a constant rate, so A itself must be a line. And you could say, well, I know that at time 0, it's 150. And at time 4, when I plug in a 4, I should get out a 10. I know it's a straight line, and so there you could just solve and that's exactly what you'll get, by the way, if you do that, right? 150 minus 10 is 140. The 140 over 4. I assume so. It better be, right? Negative 35 because it's decreasing, right? And so then you could just plug that stuff in and you get negative 30, the m is negative 35t plus 150. So, like, that's not how I derived it, right? I just said, oh look, it's getting smaller, and then I just magicked this up. But you don't need to rely on that if you're having a hard time, right? And whenever you have a constant rate, you could just say, well, what is this to begin with? Where does it end? Those are 2 points on a graph because you know the times, right? And then, just like I did, you draw it out and find your thing. Okay, so what about B? We could say this length starts at 0 and moves to 100, right? So when time is equal to 0, this length is 0 because he starts here. And then when time is equal to 4, he's up here at 100.
25. Positive.
So it has a slope of positive 25. M is 25. And it goes through the origin, so it must be the case y equals mx plus, or b equals mt plus little b would be 25t plus 0. Or you could say, well, yeah, hold up. It's moving at 25, so it has to be a 25t, because it's constant. And so, and then figure that out, okay? So, a few different ways of doing it. One way or another, we have our A, we have our B. So now let's get an equation involving A, involving B, and D. So, D of t squared is equal to A of t squared plus b of t squared. Now we have the actual values. Yeah, we could do let's do it this way. Where I'm going to go d of t squared is equal to plug in my a of t, 150 minus 35t squared plus 25t squared. Take the derivative all the way through. Chain rule, 2d times d prime of t equals, now 2 drops down, 150 minus 35t times negative 35 plus 2 25t times 25, which, like you said, yeah, works out to 50t. So, I don't want to have to get rid of that stuff. I'll just do this. There we go. Okay, so 2d d of t times d prime of t is equal to.
Now, 7.
Yeah, now here's the thing though, and this is where you could really, we only care about d at a given time, don't we?
Yeah, 4.
At 4. And so what I could do right now is say, you know what, okay, we have the relationship, so let me just go ahead and plug in my 4. D of 4 times D prime of 4, because D prime of 4 is what I care about, right? How fast is the distance changing? So in other words, we're looking for D prime at what time? At 4. Well, that's when it's 4. That's what I'm looking for. There it is. Now what I could do is say, well, I know what happens when you plug in a 4 here. That's how I derived this, right? We know that when you plug in a 4, you get out a 10. That's the whole point, right? So 2 times 10 minus 35 plus, I'm going to write that as 2 times 25. 2 times 25. And now the 25t, yes, I could plug in a 4 and get out 100. Or I could also say, well, that was that part. That's how I derived that in the first place. So I know that that's 100. The only thing we don't have is d of 4. But we do have d of 4.
Yeah.
It's 100, so it's 2 times 100.499 times d prime of 4. This works out to 4,300. It does. So 4,300. And so now I'm going to bring it back up to here. Let me get rid of this. D prime at 4 is equal to 4,300 divided by 2 times 100.499, which works out to 21.393. What are the units?
Kilometers per hour.
Good. Kilometers per hour. Good rule of thumb. Anytime you have, of course I erased it. We had this relationship, right? So this thing must have the same units as these things, which are in kilometers. And so their derivatives should have the same, you know, like if you're really cutting corners, you could just not think about it and then at the very end go, what were the derivatives there? Kilometers per hour, that's the derivative there, you know, and that's what I do. But anyway, that was a doozy, huh? So, just real quick, another way, and this is one of the nice things about using the other notation. So we knew that distance squared is equal to a squared plus b squared. One of the nice things about using the other notation is that this works out this way. Take the derivative with respect to time of everybody, and you get 2d times, well, whatever the derivative with respect to time is, equals 2a times the derivative of a with respect to time, plus 2b times the derivative of it, which is the derivative of b with respect to time. And now you're not really thinking about what do I need to plug in for t. You know that this occurs at some instant where you happen to know that a is 10, so you plug that in. You know that the change in a is 35. This occurs at the time when b is 100. And the derivative of b, which is the rate of b, is 25. The problem, though, is
It's a negative.
it should be a negative, right? So there's a pitfall there. If you're savvy and you're on top of it, you'll go, oh, it should be negative. Or should it, right? So like I said, when I first started doing these, I did functions for every single thing so I wouldn't mess it up, right? Because look what I just did, right? That's real easy to mess up, but it is a lot cleaner, right? So you have, there are give and takes with each ones of these, but yes, this should be negative right there. That's real hard to see, but if you think about it, this thing that you're calling A is getting smaller, and so it should be a negative number. So anyway, I just want to throw that up there. Questions on this one? No? Okay. This one was a doozy. I don't think the others are this bad. Right? I don't know. Let's see. I don't remember which of these I did. Okay, so this one is similar to number 30. Going back to our first, the first setup where we had the ladder falling like this. This guy's moving at 2, what did we say, feet? I think it was feet. Feet per second. And we're talking about the time when this was 4 and this was 3, the ladder was 5, okay? Given that setup, now here's the question. How fast is the angle between the floor and the ladder changing at this instant?
Which angle? The one on the bottom?
The angle between the ladder and the floor and the ladder. So here's the floor, here's the ladder, so it has to be that one right there. So there's theta, and we want to know how fast is theta changing at this instant. And that's important at this instant because, as we saw, this guy does not fall at a constant rate. This guy might be moving at a constant rate, but this coming down is not at a constant rate. So you have to know, well, when are you talking about? Okay, so anyway, so,
We're gonna be some trig functions.
oh yes we are. So, what trig function would you like to use?
Sine
Okay, so sine of theta
equals 3 over 5.
at this instant, but now we're kind of in the same problem as before when we said, okay, here's 10, here's 100, here's the thing I care about. Now we said that d squared is 100 squared plus 10 squared. Take the derivative, it just goes away. When you do this, you're not assuming movement, right? You're assuming that everything's locked in place and nobody's changing. So what we have to do then, and so whenever you do that, because that's my instinct too, right, is to say, well, look, it's 3/5 or whatever, and so on and so forth. What you have to do is say, hold up, no, there's movement, so I better give some things some names and think of them as functions of time. I'm going to use the same functions as before. I'm going to say that this movement down here is x, and so this length there is x of t. This length here is y of t. Okay? And now, given that one of those is x and one of those is y, what trig function would you like to use?
Tangent.
I think tangent. Now we could, if you wanted, you could say, well, hold up, sine of that, right? But that's not going to take him into account. And something tells me that because we have an x prime here, right, this is x prime, we're going to need an x prime in order to solve this problem, right? We're probably going to need both of them. And so I'm going to choose the one which gives me both. So you said tan theta is equal to
Y over t.
y over what?
Y of t over x of t.
There you go. Y of t over x of t. Now, is theta a function of t?
Yes.
Does theta
Yes, it
change?
changes.
Yep. As time goes on, theta changes. So really, what we have here is a theta of t, a y of t, and an x of t. So now it's asking how fast is the angle between the floor and the ladder changing. We're looking for theta prime of t at that instant, right?
Take derivative of both
So
sides.
take the derivative of both sides with respect to t. And I'm going to do this not with the theta prime of t. What I'm going to, I just want to switch it up. I'm going to say what we want is d theta dt, which is exactly the same thing, right, as theta prime of t, but I just want to change it up. So take the derivative of tangent, and what do we get?
Secant squared of theta times theta prime.
There you go. Secant squared of theta times theta prime, or d theta dt, equals
Y prime times x minus y x prime over x squared.
Okay, so now, do we have all of this info at this time? We know x is 4. We know y is 3. We already did the work to find y prime. If we didn't do the work to find y prime, we'd have to. But we know that at this time, y prime was equal to, I think it was negative 8/3. It was negative 8/3. So y prime is negative 8/3 at this time. And so, okay, secant squared theta times the quantity that we want is equal to negative 8/3. X was 4 minus y is 3. X prime was 2 over x, which is 4 squared, is 16. That works out to, oh, I didn't bother. Okay. Now, here's the question. We need theta. Because whatever this is, right, I want d theta dt. All of this stuff is going to be in the numerator. Negative 8/3 times 4 minus 3 times 2 all over 16. And then in the denominator, we're going to get our secant squared theta. But what's theta at this time?
Well, we can just say sine of theta equals 3 over 4 and then take,
Or
or
how
3
about,
over 5.
you mean, well, yeah. And so you could do any of them. So you could use any of the trig functions. I'm going to use tan theta and say tan theta is, just like you said, 3 over 4. And so then, therefore, theta is arctan 3/4.
Yeah.
Right? And so you could just write that in there, arctan 3/4. However, I mean, you could also say, well, hold up, secant squared. That's the same thing as secant squared. Secant is 1 over cosine. And cosine, we could actually find that, can't we?
Yeah.
Cosine of theta is just what? 4/5. So that's 1 over 4/5 quantity squared, or 5/4 squared. 5 over 4 quantity squared. So we could write it like this. I'm perfectly fine with this. I don't care. But you could, if you really wanted an answer, and you're probably going to need to in the back of the book, you plug that in and say, oh, then all of this works out to 5/4 squared. There you go. And then you do the work and blah, blah, blah. But that's what you find out right there.
But we also just use a calculator.
You could use it. I'd be okay with that. I mean, especially with word problems like this. Like, if you notice, I just wrote like that, you know, that's, I used a calculator to find that, right? So that's fine too. But yeah, and that's the idea, right? Just, once you set up your equation, you should, well, as you're setting this up, you need to think, like, what am I given, right? Like, if we set this up without an x prime, right, or without an x in it, like if we did 3 over 5, like sine theta 3 over 5, we would not have enough info to, well, actually, we probably would. It's just, it's, yeah. So, it would work, wouldn't it? It probably would work. We'd still have to have y prime. But anyway, all right. I'm just going to shut up. All right, any questions?
No.
Okay, I just want to do a quick one with trig stuff here. Oh, man. All right. Oh, man, are we going to have time? Oh, I don't have time to get through all of these. The trough question. Everybody gets a trough question when they are in calculus. A trough is 10 feet long. The ends have, I'm not going to write all this down because we're running low on time, but it says the ends have shapes like isosceles triangles. And so this is your trough. It looks like this.
Yeah.
right? It's 10 feet long in this direction. 10 feet that way. Okay, then it says, isosceles triangles that are 3 feet across the top, so 3 feet this way on that triangle, and it says 1 foot in this direction. So I've not drawn that to scale, right? But that's the idea. Okay, and it says, if it's being filled at a rate of 12 cubic feet per minute, 12 cubic feet per minute, how fast is the water level, how fast is the level rising when the water is 6 inches deep?
1.5 times 10 would be the area of the triangle. The volume of.
Yeah, well, hold up. So I'm imagining, okay, here's the water level. Okay. Now, notice this is gonna mess you up. It's the level of the water is not 6. 6 inches. Everything else was given in feet. And if that's 1 foot, then the water level is 0.5 feet. Or we could convert everything to inches, which seems like a real pain, right? So it'd be easier to convert this one thing when it's 6 inches deep, when it's 0.5 feet deep. Okay, so let's think about this. You have your water level, blah, 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 blah. There's your water level. It's rising, okay? Now, what we want, it tells me filled at a rate of, gives me a volume per time. So I want to calculate the volume of this thing, but not here, but at any given time. So this is what we need to think about. And this is in general what you want to do. And if you've noticed, we've done this every time. Like because every time we said, oh, it's when this is 10 and when this is 100. Oh yeah, and then there's no variable. There's no t to take a derivative of, right? It's the same thing here. If we just figured out everything when it's exactly 0.5, or I'm going to rewrite that as 1/2, because 0.5 drives me nuts. So if we just figured that out, we wouldn't have any variables. So we need to think about a variable, and what's happening is we care about the level rising, so let's make that level our variable. This level right here, from here to here, that distance, I'm going to call it h for height. And when it's h, now we need to know, I want volume as a function of h. So, how do we find the volume? So this is going to help you, especially later in this class. Think about volume as an area times the length. The length in this case is going to be that depth right there, which is going to be 10.
So it's just the area of the triangle.
There you go. And so that's 10. And so the area of that triangle is now a function of h, because it depends how big h is. This, I don't know if we've ever done this before, but this is a case where you want to use similar triangles. Since you know that this width is 3 and that this height is 1, then 1 is to 3 as h is to, I'm going to call this b. Because a triangle, we know that the area of a triangle is 1/2 the base times the height. And we know that 1 is to 3 as h is to b. H is to b. So now we can get everybody up here. I'm going to bring b upstairs, bring 3 upstairs, like that. Yeah? And I want, as a function of just h, okay? And so instead of b, I'm going to have 1/2 3h times h. Does that make sense? That's the area of this right here. And so that is a function of h. That's 3/2 h squared is the area as a function of h. And so that's what I want right here. Everybody, you got that?
Yes.
Okay, so the volume as a function of h is the area as a function of h times the constant length 10. The area as a function of h is 3/2 h squared times 10. The volume as a function of h is 5 times 3 is 15 h squared. Yeah?
Take the derivative.
Now, okay, so here we go. Now, I'm going to get rid of all this.
Oh, we need to multiply.
Because let's see what it asked me for. So first off, we know that V of h is equal to 15h squared. Now, it gave me the rate. It gave me the rate that the volume is changing. It told me that V prime of h when h is 1/2, right? This means that h equals 1/2 at that time. So V prime at 1/2 is equal to 12. That's nice.
Oh.
But it's asking how fast is the level rising. So in other words, and the level is h. So what this is asking is
H.
what is h prime at that time? Or what is dh dt when h is 1/2? That is what we're looking for. So can we find dh dt from here?
Yes.
Yeah. We're going to take the derivative of both sides with respect to t. We get dv dt equals what?
38 times
30h times
H
h prime dh dt. And now it
Solve for H.
told us it's not h that we want.
H prime.
H
Solve for
yeah, h prime. And so, well, first off, dv dt it told us is 12, right? At that time. I'm really mixing up notation here, which is bad. Dh dt. It also told us that h is 1/2 at the point we care about. So h is 1/2 here at the point we care about. So we get 12 equals 15 dh dt. Therefore, dh dt, the change in the height, the change in the level, is 12/15 or 4/5 at that time. Woo! This is rough stuff. It is not for the faint of heart. There were others, but I mean, I think the only others I was going to do, there are examples that are very similar. Like example 5 is similar to one I was going to do. And what's the other one? Oh, the baseball diamond. The baseball diamond. That's a cool one, but we just don't have time, I don't think. 'Cause we're way over. Yeah. Okay. So, all right, you good?
Yeah.
All right.
Yes.